Hello everyone, welcome to this course on software defined radio hands-on for communication systems design. I am Professor Suraj Srivastav from the Department of Electrical Engineering at IIT Jodhpur, and in the last lecture we had seen the basic concepts of DSP, and in this lecture onwards we will start the Simulink hands-on. So in this first lecture we will look at the fundamentals of sampling through Simulink and will verify the concepts which we had studied in the lectures. So if you open the MATLAB, this is the MATLAB, and you see this is a workspace where you can see the different variables. This is the command window where you can write the commands and check the results. And this is our Simulink tab. So if you want to open Simulink, we'll open it from here. And this is the add-ons tab which I had described in the slides. So if you want to install a new package or any other package which is not there in your current installation, you can open it from here. So let's go to the add-on tab. So once you open the add-on tab, then you will see the search box here and you can search for the packages which you want to install. For example, I told you that during the SDR hands-on, we will require some packages from the SDRs. So you can search for RTL SDR and you will see the communication toolbox support package for RTL SDR. You can open it and then you will see this page. And since this package is already installed in my system, then that's why I'm getting installed here. But in other cases, if you have not installed it yet, then you will get the install button here, which you can use for installation. Similarly, you can search for other SDR packages, for example, USRP. So you will see communication toolbox support package for USRP radio. So this also you can open and install it. If you want to use the ADLM Pluto SDR, so you can type for ADLM Pluto SDR and you will get this communication toolbox support package for ADLM Pluto SDR, which you can install. So right now this is not installed in my laptop, so that's why I am getting the install button here, which you can follow and install. So this is about the installing various packages. Now we will start with our first Simulink model. So we will practice the exercises which we did in the last lecture on sampling. So I'll also parallelly open the slides. So if you recall from the last lecture, we had discussed the basics of DSP and we started with the sampling theorem. And we had seen first that if you have a sinusoidal signal, then its spectrum is the spectrum contains two delta functions, one at f0 and one at minus f0. So let's start with this exercise first. Now to start Simulink, I'll click here on the Simulink button. So it will open this Simulink tab. And I want to start with a new model. So I'll create a blank model, create model. So this will open a blank Simulink model where you can start adding the blocks and then you can run it to verify the results. So this is a blank Simulink model, and first you can, before adding anything, you can first save this with a name. So I'll add this with sampling 0. So now this model is ready to start. You can, so what we would like to do in the first exercise, we'll take a sinusoidal signal and then we will use sampling there, and we would like to see how does the sampled version of the signal looks, how does its spectrum look. If it satisfies the sampling theorem, then how it looks, and if it does not satisfy the sampling theorem, then how does it look. So to this let's start a sine wave block. So we'll add a sine wave block from DSP systems toolbox under sources. So let's add a sine wave block. I'll increase the size. So this is the sine wave block, and after adding it here, so you have to configure it. So let me just repeat how did I add this block. So just double click here and then you will get search blocks, and here you type sine wave. So, you will see several sine wave sources. The one which we have taken is from the DSP system toolbox sources. So, we just click here, you will get the sine wave block. So, this is how I got this sine wave block, and then if you want, you can further zoom it, you can increase the size for better visibility. So, this is how you will get a sine wave block, and then we have to configure this sine wave block. So, double click here, you will get a sine wave configuration block, and you can configure this block. So, let us see the parameters one by one. The amplitude of the sine wave is 1. So, this block will generate a sine wave from -1 to +1, that is the range. Currently, the frequency is 100 hertz. So, let us make it 1000 hertz. So, frequency I have set to 1000 hertz, phase offset is 0, and sample mode is discrete. Output complexity is real because initially we want the real sine wave. So, the output complexity is real. Computation mode is trigonometric functions, and sample time. So, this is the important parameter. This is what we have to carefully look at. Now, sample time right now is 1000, 1 over 1000. So, that means the sampling frequency is 1000. The relation between the sample time and sampling frequency is Ts is 1 over Fs. Ts is the sample time. So, Ts is 1 over Fs. So, here in this case the Fs becomes 1000. So, right now the sampling frequency here is 1000 samples per second. So, I will increase it, I will make it 10,000. Okay. And this is the samples per frame. So, right now I will not go into the details of all these parameters, but slowly you will explore these things. Let us make it 1000 samples per frame, apply. So, let me just show you the parameters once again. Frequency I have changed to 1000 hertz, and sample time I have made it 1 over 10,000. So, that means the sampling frequency has become 10,000 or 10 kilohertz. Samples per frame also I have increased to 1000. So, as we go along, I will explain you some of these parameters. So, this is my sine wave. You can also rename it with 1000 hertz sine wave. So, this is the source which we are generating, 1000 hertz sine wave with sampling frequency of 10 kilohertz. Now, first we would like to see it in the time scope. So, we will add a time scope here. So, search for time scope, again just do a double click, you will get this search block, type here time scope. So, you will get DSP systems toolbox, under sinks you will get time scope. So, take it, this is my time scope. And now it will connect these two blocks. So, to connect these two blocks, just put your mouse cursor here, it will allow you to add these two boxes, right. So, this is how you can connect it. So, now this is the sine wave, and we will be able to see the output of this sine wave in this time scope. Okay. For running the simulations, you can also adjust the stop time. So, right now you see that stop time is 10 seconds, but if you want to run it for smaller duration, you can set it for 1 second. So, this simulation will be run for 1 second, and the sine wave for 1 second will be displayed here in the time scope. So, after building this model, let us save it, and then you can run it from this run button. So, when you run this using this run button, it will run this Simulink model and it will show you the output. So, you see we get this kind of output. This is for the output of the sine wave block, and you see this is the kind of plot you will see. and this is a 1000 hertz sine wave. So let's verify whether this is actually a 1000 hertz sine wave or not. So to see this closely, you can first see the axis. This axis is in time, seconds. So that means this is 0.1 second, 0.2 second, 0.3 second up to 1 second is this point, and this is the amplitude of the sine wave. Now to look at this thing closely, you can use this zoom button here. You see this zoom button. So go to this zoom button and then you select the area which you want to see. So let me select this area which I want to see. So this is the sine wave. Now further let's zoom in and verify. So just zoom in further and you see this is the sine wave. Alright. Now if I ask you what is the frequency of this sine wave, how will you calculate? So you will see one complete period and then you will identify what is the duration of one complete period, and based on that you can compute what is the frequency. So if you look at this point, let me take this point. This point is 0.35 seconds, right? That means this is 350 millisecond, and then this point is 351 millisecond, right? So from this point to this point is 1 millisecond, and you see we are the sine wave is completing one complete period in 1 millisecond. That means this sine wave represents a 1000 hertz sine wave, right? So this is how you can verify the sine wave. Let me just rerun it once again. So this is the sine wave which we have got, 1000 hertz sine wave, and you can click here on the zoom button and then you can zoom a further small section and verify what is the duration. Once again you see this is 384, this is 385 millisecond. So that means this one cycle is completed in 1 millisecond. So the frequency is 1000 hertz sine wave. So this is the first, just an example to demonstrate how can you generate the signal in Simulink and how can you verify or how can you visualize this in the time scope. So this is the first exercise. Now we'll add few more things, and we are mainly interested in looking at the verifying the sampling theorem. So let's open this box again. So let's closely look at this thing. What are the parameters right now? The sampling frequency is 10 kilohertz, 10,000 hertz, that means 10 kilohertz. So we are taking 10,000 samples per second. So this is our Fs. Fs is actually 10,000. So as you know from the yesterday's lecture, I'll just come here again. If your sampling frequency Fs is there, and then your fundamental period becomes minus Fs by 2 to Fs by 2. That means in the range of minus 5 kilohertz to 5 kilohertz, you can represent a signal without any aliasing. But outside this frequency range, there will be aliasing. Okay, so that means now we have to start looking at the spectrum of this signal, and then we would like to see the spectrum of the sampled signal. So what we have to do here, if you want, so this was the time domain analysis of this signal, and we had verified the frequency of the signal. Let's also add a spectrum analyzer here. So let's add a spectrum analyzer. So again you will just type spectrum analyzer and you will see spectrum analyzer under toolbox, DSP systems toolbox, sinks. So let's open this. This is the spectrum analyzer, and now we'll look at the spectrum of this sine wave. So again you can drag this block here and you can connect it with the output of this sine wave block. This is our spectrum analyzer. Save this model and run it. So now the time domain analysis we have already done. I'll close it. Let's open the spectrum analyzer. Now what do you see here? First of all, the important thing to verify is that, as we mentioned here, if you sample the signal at frequency, sampling frequency Fs, the fundamental frequency range becomes minus fs by 2 to fs by 2. In our case, our signal is sampled at 10 kilohertz. So fundamental frequency range becomes from minus 5 kilohertz. You see at this left side we have minus 5 and we have 5 kilohertz. So this is the range from, this is the fundamental range, minus 5 kilohertz to 5 kilohertz. And then you see two peaks here. And these two peaks correspond to f0 and minus f0. This is what we had seen yesterday. If you have a sinusoidal signal like this, the spectrum of this signal will have two peaks, one at f0, another at minus f0. That is what you see here. These are the two peaks you see in the spectrum of the signal. And where are these peaks appearing? One is at minus 1 kilohertz. You see the range is minus 5 kilohertz to plus 5 kilohertz, and this point is minus 1 kilohertz, and this point is 1 kilohertz. So you see these two peaks appearing at minus f0 and f0. So this is the first thing which we discussed yesterday. Now we want to revisit the sampling theorem, and we want to verify this result. If the frequency of the signal is less than fs by 2, then there will be no aliasing. That means the sampled version of the signal, remember when you design this block, so sample mode is discrete. That means the output of this block is giving you discrete time signal. That means it is giving you the samples of the signal. Okay. So already the sampling is being performed here in this block. 1000 hertz is the frequency of the sine wave and sampling frequency is 10,000 hertz. So the output is the sampled version of sine wave. Now let's verify this result. So currently if you verify, first thing is that your fs by 2 is 5 kilohertz and your input signal frequency is 1000 hertz, which is less than 5 kilohertz. So there is no aliasing, and you see the spectrum of the signal at minus 1 and 1. There is no aliasing. This sampled version of the spectrum also represents the actual sine wave, the spectrum of the actual sine wave. If you further increase it, let's make it frequency 4 kilohertz. Apply and OK, and I'll just remove this thing. Or I'll just make it 4 kilohertz. This is the 4 kilohertz sine wave. Still 4 kilohertz is less than 5 kilohertz. 5 kilohertz is your fs by 2. So you should be able to recover the sine wave exactly. If you look at the spectrum of the signal, there is the time scope, and you see the peak coming at 4 kilohertz and at minus 4 kilohertz. Still the fundamental range is minus 5 kilohertz to 5 kilohertz. This signal is within the fundamental range, so there is no aliasing, and you are able to recover the signal as it is. Or basically we are not recovering the signal here, we are looking at the spectrum of the signal, and the spectrum of the sampled version of the signal is representing the spectrum of the original signal. Now let's move to the interesting case. If your frequency becomes higher than 5 kilohertz, and the example which we took yesterday is this one. So if f0 is less than 5 kilohertz, this was the example, we already verified there is no aliasing. But what if f0 is 8 kilohertz or f0 is 23 kilohertz? So we verified that if f0 is 8 kilohertz, the sampled version of the signal will take identity of 2 kilohertz, and if f0 is 23 kilohertz, the sampled version will take identity of 3 kilohertz. So let's verify this part. For this we have to change the sine wave here. The frequency of the sine wave. So first I'll make it 8000, apply, OK, save it and then run it. We'll closely look at the time domain version once again, but first you look at this frequency domain version. Now the input frequency is 8 kilohertz, correct, which is higher than 5 kilohertz. So you see what identity it takes. It takes the identity of 2 kilohertz. Although the original signal is at 8 kilohertz and you have sampled it with 10 kilohertz, but the identity which it takes in the range of -5 to 5 kilohertz is 2 kilohertz, right. So, this is what we verified yesterday using the sampling theorem result. So, the 8 kilohertz signal appears as 2 kilohertz in the fundamental range. Now, similarly, you can also change it to 23 kilohertz. There is a 23 kilohertz frequency, and save it and run it. And what do you see? The original frequency, the continuous time domain signal, has frequency 23 kilohertz, but when you sample it with 10 kilohertz sampling rate, which is insufficient, so there will be aliasing, and due to this aliasing, this 23 kilohertz range, the frequency takes the identity of 3 kilohertz. You see the two peaks at -3 and 3. So, this is what we discussed yesterday, and we have now verified it. Now, another quick example which we want to do is related to, so for example, if you see 23 kilohertz, so 23 kilohertz sine wave takes the identity of 3 kilohertz, and we had verified that if you have 8 kilohertz sine wave, that takes the identity of 2 kilohertz. So, we would also like to see this thing and verify this thing in the time domain. So, to do this, we will add, or we will just look at the spectrum of the 8 kilohertz sine wave and 2 kilohertz sine wave in the sample domain. So, I will create a new model for this. So, I will open a new model. So, from here you can open a new model, this, and save it with a name sampling_1. So, what I will do now, I will create a 2 kilohertz sine wave and 8 kilohertz sine wave, and I would like to see the sampled version of them and want to verify whether they look identical or not, because in the frequency domain you have already verified that 8 kilohertz sine wave takes the identity of 2 kilohertz sine wave. So, that is what I want to verify. So, let us add a sine wave block. So, again I will just repeat it, do a double click here, and then you will get this search block, type for sine wave. So, this is my sine wave DSP systems toolbox sources, configure it. So, we will keep this frequency as 2000 hertz, and sample time I will set to 1/10,000 because the sampling frequency is 10 kilohertz. Samples per frame, again I will set it to 1000. Apply, OK. And I will do one more slight change. I will keep the phase offset as pi/2. So, that means this is generating cosine 2 pi f naught t, because we have set the phase offset as pi/2. Sine wave shifted by pi/2 is the cosine wave. Now, this one is the frequency with 2 kilohertz. I will create another sine wave which has frequency 8 kilohertz. So, you can copy this block, Control C, Control V, you can do copy it block, or you can also right click here, copy, and then right click again and paste. So, this will create a copy of this block. So, this is a similar block, but I would like to configure it with 8 kilohertz sine wave. So, now we have two sine waves. I want to see both of these sine waves in the time scope, and I want to verify whether the sampled version of these two sine waves look identical or not, because in the frequency domain we have already verified. I will add a time scope again here, DSP systems toolbox syncs. From there I have taken the time scope, and maybe I will zoom it further, these boxes. Now, I want to see both of these two sine waves in this time scope. So I will first configure it. So open this time scope block and go to this settings, and I want to take two input ports, one for the 2 kilohertz sine wave and another for the 8 kilohertz sine wave. So I will make the input number of input ports as 2, and I will also put the layout in 2 rows. So just select first and second, apply and OK. So now you see there are 2 rows created. One will be for the 2 kilohertz sine wave and second will be for the 8 kilohertz sine wave. And you will also see 2 ports here. So now what I will do, I will connect this output here in the first input of the time scope and this output here in the second input of the time scope. Save this model, and you can also modify the time, stop time. So I will again keep it for, let's say, 2 seconds. And run it. So you see this is the time domain version of the first one is for the 2 kilohertz sine wave and this one is for the 8 kilohertz sine wave. And now we want to verify it closely. So let's zoom it further and see it, because this axis is, remember, this is in seconds. So let's zoom a small section of this time scope and verify. I'll further zoom it. I want to see few cycles and verify whether they look identical or not. And you see they are exactly same. First one is the sampled version of 2 kilohertz sine wave and second one is the sampled version of 8 kilohertz sine wave. But when you see in the sample domain, the discrete domain, they look exactly same. And that is why this 8 kilohertz sine wave takes the identity of 2 kilohertz. And why does it happen? So let me just zoom it further. Why does it happen? So if you look at the first sine wave, 2 kilohertz sine wave, this is completing one time period in this duration point. It starts from here and completes one cycle in this duration from here to here. This is for the 2 kilohertz sine wave. But the 8 kilohertz sine wave actually will complete many more cycles in this, right? Because the 8 kilohertz sine wave has higher frequency in the continuous time domain. So it should complete many more cycles in this time duration because it is of higher frequency. But since we are sampling the signal at regular intervals, so at the points where we samples the signal, there it matches with this, right? So in between there are some cycles being completed, but because we are missing those cycles, so we are getting the sampled version of the signal which looks like this. So the reason behind 8 kilohertz sine wave looking identical to 2 kilohertz sine wave is that within one sample duration, this is one sample and then another sample is coming here. So within one sample duration, we are missing few cycles of the 8 kilohertz sine wave, and we are missing it in such a way that the overall identity looks like the 2 kilohertz sine wave. So this is the fundamental reason, and you can also write it mathematically and verify it. We will not go through it, but you can actually do it and you can write it on paper and verify it, that 2 kilohertz sine wave will take identity of 8 kilohertz sine wave if you sample it with 10 kilohertz sampling frequency. So this is the second exercise on sampling. Thank you everyone. So let's stop here and let's meet in the next lecture with the sample rate conversion.